Okay, mean value theorem. Ladies and gentlemen, this is the third and final of the major theorems we're learning in calculus. So we have intermediate value theorem, which is a height between two heights, right? The function is continuous. We have one height, we have the other height. That means we'll cover every height in between, right? We have extreme value theorem, which was section 1 of this chapter, right? That means on a continuous function, there's a maximum and there's a minimum, right? And we use a candidates test for that. Okay, this is the mean value theorem. What does mean mean? The average. So the average is going to equal something. Okay, average is going to equal something on this one. All right. 3.4, mean value theorem, which we also call MVT. The MVT. If f is continuous on the closed interval, okay, we've seen that before, right? Those functions have had to be continuous on the closed interval for those previous functions or those previous theorems to work, correct? And it has to be differentiable on the open. So f also has to be differentiable on the open interval a to b. Then there exists a number c, which is an x value on that interval a to b, such that f prime of c equals f of b minus f of a all over b minus a. What in the world? Guys, what is this f of b minus f of a? What is that in general? Slope of what? Between what? 2 points. And what have we called this before? Slope of secant. Where else? But now we have endpoints. A and b. It's final. Average what? Average rate of change. Yeah. The average rate of change. What have I called this before? The average rate of change equals. So the average rate of change over some interval, right, is equal to, and what's the derivative? What is that derivative? Evaluated at a c value. What is that? Slope. What else do we call that? Slope of the tangent line. What else? In terms of rate of change. Instantaneous rate of change. Now we've actually seen that once or twice. Instantaneous rate of change, and you just found the derivative at a value, right? So AROC equals IROC. The average rate of change equals instantaneous rate of change. So that's the mean value theorem. It says that there exists some value c such that on a closed function that is continuous on a closed interval and differential on an open interval, there exists some value c such that the average rate of change equals instantaneous rate of change. All right. So mean value theorem, AROC equals IROC. What does that look like, guys? Well, let's draw a graph, since we've done that quite a bit. How would that look? Okay. Let's kind of use like a cubic function maybe. Ooh, that's close to not being a function anymore. Okay, if this is a... that's just bugging me. I'm going to fix it. There we go. This is B. The average rate of change would be, we'll use red, will be the slope between the beginning and end point, right? This is AROC. That's the average rate of change. Doesn't matter, all these dips and valleys, doesn't matter. Like, what's your beginning position and ending position, right? So what's the average rate of change between those 2 points? That slope of the secant line, basically. Okay. What would instantaneous rate of change be? Slope at an instant, right? Slope at a tangent. Slope of a tangent. Tell me where to stop. Where would that occur? As I fall along this graph, where would that occur? Right there? So what are you guys looking for? No, why'd you pick this spot? Yeah, they're parallel. Yeah, so they're supposed to be the same. They have to be parallel, right? Since they're both slopes, average rate of change is a slope. Instantaneous rate of change is a slope, right? You're looking for these lines to be parallel, okay? Okay, does it happen again? Right here? We good? It's all approximate right there, right? Well, Mr. Bondley, this says 1 C value. Could there be more than 1? Could there be more than 2? Could there be more than 4? I mean, we could have a whole bunch, right? Okay, so these would be our IROCs, instantaneous rate of change. So that's the major idea. This is what our theorem tells us. It tells us it occurs. Now what we have to do is find that C value. That's what they're going to ask us to do. Okay, let's take a couple problems and we'll figure it out. Just think how far we've come though, guys. If we think about this cubic function, what do you guys know about the first derivative right here? First derivative is greater than 0, which means the function is increasing. What's happening right here? Relative max, okay? We know that the first derivative equals 0. The first derivative changes from positive to negative, right? What else do we know? What? Concavity, what do you mean about concavity? Point of inflection, where? Tell me when to stop. Right here? Do you want me to stop right here? No. No? Yeah. I would. Well, it looks like we have concave down right here, right? And then concave up pretty much. And then almost concave up right there too. Now, this could almost be a questionable graph because this would, questionable. I would question maybe the differentiability right here. Like, seriously, Bonnie, figure it out, draw a better graph. Okay, you can almost argue that I'm concave up right here, then concave down. So we'd have to analyze the function a little better. Okay, a lot of stuff we know. What would be the absolute max of this graph? At B? Right here? F of B would be the absolute max? What would be the absolute min? It'd occur at A. What would be the max or min, I mean? F of A. Give us a height, right? Okay. All right. A lot of review stuff. It's good stuff. Okay, here we go. Determine if the mean value theorem applies to f of x equals x squared minus 5x plus 7 on some closed interval -1 to 3. State thoroughly the reasons why or why not the theorem applies. If the theorem does apply, find the value of C guaranteed by the theorem. It is extremely important for us to state that those two qualifiers are true for us to apply the theorem. If we don't, we might get the whole problem wrong. Okay? Keep an eye out for that. Nice thing is, though, again, when we're learning something new, we try and use friendly functions. So we will focus on the process, not the difficulty of the derivative. Later on, we'll worry about the difficulty of the derivative. This is going to be a, Is this function continuous on -1 to 3? Why? What type of function is it? Polynomial. Okay, so we can, like, it's common knowledge that polynomials are continuous, right? We can state that, but we have to state it. So f of x is a polynomial. Therefore, f is continuous on the closed interval -1, 3. Now, what else do we know about polynomials in terms of differentiability? Are they differentiable everywhere?
Yeah.
Yeah, they're smooth, they're continuous, and they're smooth, right? So they're differentiable everywhere. We can just state that, and that's a good enough reason. We just have to make sure we say the function is continuous and differentiable on the open. And therefore, MVT applies. Okay, we check to make sure we can apply the theorem, and then we execute some calculus and some algebra so we can find those C values. Big idea for mean value theorem is that the average rate of change equals the instantaneous rate of change. Well, let's figure it out. Let's find the average rate of change. F of 3 minus f of -1 all over 3 minus 1. And I'm going to put a note here, since this is the first time we've done this. This is AROC, average rate of change. F of 3, or I'm not going to try and cut too many corners, so I'm just going to write everything out. 3 squared, 5 times 3, plus 7, minus big parenthesis, -1 squared, minus 5 times -1, plus 7, all over 3 minus, I made a mistake there, didn't I? -1. Okay, subtracting negative, same thing as adding a positive. 3 plus 1 is 4. All right, let's figure out what's in the top. Okay, what was that? 9 minus 15 plus 7. Okay, -1 squared is 1, so subtract 1. -1 times -5 is 5. Minus 5, minus 7. All over 4. Okay, sometimes we don't have our calculator available to us, right? We gotta be able to do this stuff pretty quickly. So, and like I said before, is if you just write it out and then do the work, it saves time instead of just trying to think about it. For most of us, anyways. Okay, plus 7 minus 7. What is that? Was that minus 6? Minus 6 more? -12 then? So our average rate of change on those endpoints is -3 on those endpoints while bonding. So our average rate of change is -3. We got to find our instantaneous rate of change, which is our derivative, and set it equal to -3 then. Okay, so let's find our derivative. F prime. Okay, real quickly, was that 2x minus 5? There's our derivative. We want our average rate of change to equal the instantaneous rate of change. So 2x minus 5 equals -3. So our slope of a tangent line has to be -3. We've done that before. Okay, 2x equals, what would that be? X equals, so what's our C value? 1. So C equals 1. Again, C is that X value such that AROC equals IROC. C equals 1 guarantees MVT on the closed interval, -1 to 3. Good enough. Any questions on this? It is something we've kind of done before. We've asked you guys to find when is a slope equal to a number. Well, that number now is just an average rate of change. Okay. Make sure we set up our qualifier statement before we apply. Well, Mr. Bonley, what if this function is not continuous on the closed interval? Then you say, the function is not continuous on the closed interval, therefore MVT does not apply. We are done with the problem. Move on to the next. That's all you got to do. Okay? That may or may not happen in your homework. All right, determine, again, if the mean value theorem applies to a little bit more of a difficult function. Got to keep an eye out for some stuff. On the interval 1 to 2, state thoroughly the reason why or why not the theorem applies again. If the theorem does apply, find that value of C. Okay, when is this function maybe not continuous or defined? Is 0 on that interval? Nope, so we don't have to worry about it then. So the only time when this reciprocal function is not continuous would be at x equals 0. Therefore, this function is continuous on 1, 2. And you guys remember reciprocal functions, where they look like this, something like that. Or if we reflect it, oh, that's bad. Looks like this. Oh, we can move it side to side or up and down, right? So the only value that these functions are not continuous at is when the denominator equals 0. But since they are smooth also, what do we know? We know those functions are differentiable at every value except for when the function is not continuous. Okay? So since 0 is not in this interval, we can just state f is continuous on 1, 2. And because we know these reciprocal functions are smooth, we can just state it is differentiable on the open interval. And then therefore, MVT applies. Okay, what are we looking for mean value theorem? Equals to instantaneous rate of change. Now, what they could say, does the average rate of change equal the instantaneous rate of change? You got to remember, oh, that's mean value theorem. Even though they didn't specifically state that we want the mean value theorem, you better make sure it can be applied. Because if they ever ask you, when is the average rate of change equal the instantaneous rate of change? That is mean value theorem. You better make sure you can apply it first. Okay? All right, let's find the average rate of change. F of 2 minus f of 1 all over 2 minus 1. And that's just the slope between 2 points, right? Average rate of change. Okay, was that 6 over 2 minus 3 minus 6 over 1 minus 3 all over 1? 6 over 2 is what? 3. 3 minus 3 is 0. 6 over 1 is 6, minus 3 is 3. So 0 minus 3, negative 3. Coincident. All right, what's our derivative now? Well, before you do that, you probably want to rewrite. I would do that. Do a classic rewriting skill. Use your classic rewriting skills. Make this function easier to differentiate. Okay, f prime then, would that be negative 6x to the negative 2 power plus 0? Okay, here's our average rate of change. The average slope between those 2 points is negative 3. Here's some instantaneous rate of change on all values of x except for 0. We got to find out when it's negative 3. So negative 3 equals negative 6 over x squared. Taking the liberty of simplifying while we're writing this out. All right, solve for x. I'm going to go negative 3x squared equals negative 6. And x cannot be 0. That's why we can multiply by x here, right? Divided by negative 3, x squared equals, would that be 2? Therefore, x equals plus or minus square root 2. Okay, so what's our c value or values? Include both of them? Why no? Why yes? Yeah, even though we came up with 2 of them, let's not include both of them because we're not in the interval 1 to 2. Okay, square root of 2, well, square root of 1 is 1, square root of 4 is 2. So if we had square root of 2 or square root of 3, we're in between this interval, right? So we're just going to state, we're only going to look at x equals square root 2 because negative square root 2 not in 1 to 2. I'm just going to make that little note. Give a reason why I'm not including one of those values. Okay? And now let's write a concluding statement. C equals square root 2 guarantees MVT on 1 to 2. Close interval. Questions on this? Because they're asking for the mean value theorem on the closed interval, I would use closed interval in this one. It does matter on saying continuous and closed and differential in the open. These matter actually because we're talking about domains. And if we were talking about increasing, decreasing, I'd say just use parentheses all the time. Or concave up, concave down, just use parentheses all the time. Okay? All right. You okay with this one? Okay, I got one more example for us, trig one. And then we're going to look at when MVT does not apply. Okay, MVT. If we have this function f of x equals sine 2x plus cosine x, is this function continuous and smooth? What do we know about sine and cosine? They're just continuous and smooth, right? So if you take 2 continuous smooth curves, add them together, you get a continuously smooth curve. Okay? Therefore, it is differentiable and continuous. So continuous on the closed, differentiable on the open. So f is continuous on 0 pi and differentiable on 0 pi. Therefore, MVT applies. Now just execute MVT. Find out where the average rate of change equals instantaneous rate of change. So we're going to find f of pi minus f of 0 all over pi minus 0. Just writing this out could score you 1 point on the FRQ. All right, got the bottom. The top would be what? Sine 2 pi plus cosine pi minus sine of 0 plus cosine 0. All right, let's do this without a calculator. Sine 2 pi is what? Cosine pi minus sine 0, cosine 0, and we're thinking widths and heights, right? What's your width at that value around that circle? What's the height at that value around the circle? Ooh, this was close to being 0. That would have been nice, but it's -1, -1, so -2 over pi. All right, let's find the instantaneous rate of change for all x's. F prime x. Okay, that'd be what? Cosine of 2x times 2, right? Using the chain rule, put that 2 in front right away. Derivative of cosine will be negative sine of x. We need to figure out when our derivative equals our average rate of change. And I'm going to use a calculator on this one, which means you guys are going to use a calculator on this one. So either add that 2 pi to the other side and find your zeros, but I think it's easier to enter in negative 2 over pi into y1, enter this other function into y2, find the intersection. Okay, make sure you change your window. I only want to be looking at 0 to pi. Everything else I don't care about, unless you want to sit here and try and find every single time it crosses. It's kind of what you guys have, right? Something looks similar to that. So we go to calculate intersect. First curve, second curve, arrow towards the intersection a little bit. Is this right? 0.345. No? What do you get? Anybody? Be brave.
I got 0.770.
770 looks good to me. How about this other one over here? .371. I believe that works for me. Okay. C equals 0.770 and C equals 2.371. Guarantee. MVT on interval 0 pi. I like doing like this. Yeah. All right, we good? Use your calculator pretty easily. All right, now let's see when MVT would not apply. There's a couple of reasons why MVT would not apply. And so what we need to do is explain precisely why we cannot apply the mean value theorem. Either of the 3 functions provided. All right, part A. Ooh, absolute value functions. What do we know about absolute value functions? Number 1, are they continuous? Okay, so f is continuous, okay. F is continuous on that closed interval. Are all absolute value functions differentiable? Everywhere, I should say. Where is this function not differentiable?
At 3.
Why at 3?
Because x minus
Yeah, we want to find out when this absolute value equals 0, right? Well, you don't have to find the derivative. We just know right away these absolute value functions are not differentiable when the absolute value is 0. Okay? Well, that happens when x equals 3. Is 3 on this interval? Yeah, buddy. So f is not differentiable at 3. Not differentiable at x equals 3. That's being precise and specific. Therefore, f is not differentiable on the open interval to 5. And then finally, MVT does not apply.
Why would it be differentiable, not
What do you mean?
just like
Right here?
zero? Yeah.
That's where that sharp point's going to occur. When the inside of here equals 0, that's where that sharp point's going to be at. Because that's going to be a horizontal transformation, sliding it left or right. Okay? And this right here is essentially sliding it up and down, right? Just by a growth factor also of x. How about part B? Is this function continuous on -3 to 1? Where is this function not continuous at? There we go. Let's state it. F is not continuous at x equals -2. Therefore, F is not continuous on the closed interval -3, 1. Ah, thank you. G. G is not continuous. Therefore, MVT does not apply. Mr. Bonley, why are we not saying this function is not differentiable? Well, what do you know about functions when they're not continuous at a value? They're what? Exactly. If you're not continuous at that value, you cannot be differentiable at that value. Okay, so that would be being redundant. How about C? Well, you're taking the cube root. That'll be okay for a negative value. Well, cube root looks something like this. What if you square the cube root? What happens to this portion? It goes positive, right? It reflects. Is the function h continuous on -3, 3 closed interval? I don't see any holes in the graph, do you? So it's continuous. Let's state it. F is continuous on, jeez, thank you. Good thing somebody's paying attention. H is continuous on -1 to 3. Okay, good. H is not differentiable at x equals 0. Therefore, H is not differentiable on the open interval -1, 3. And that means MVT does not apply.